One-time pads are the strongest form of encryption that we can use. One thing that's really interesting about them, in my opinion, is that this encryption algorithm can be done by hand. It's unbreakable. If you encrypt something securely with a one-time pad, the greatest cryptographers in the world aren't going to be able to break your message. But that doesn't mean it's perfect for every single use case. One-time pads were and potentially still used by spies for transmitting messages. If you're a spy and you still use one-time pads, go ahead and let me know. I'd love to hear about your experience. Somehow I doubt that any spies who might be watching this are going to tell me about their use of one-time pads. But hey, let's get into it. This is similar to the Caesar cipher in that we're rotating, or it's like we've got our super secret dial that we're using, but instead of using the same rotation on our super secret dial every single time for every letter in our message, we're using a different rotation every single time. So that rotation is the key, and we have multiple rotations. So our key needs to be as long as the message. So here we've got an example. Took this from Wikipedia. This was a page from a code book from the National Security Agency. Essentially on the left here, we've got random letters. So they're the letters A through Z, but a random number generator, or a random letter generator in this case, just put letters here with no pattern. So imagine you had just a bucket of like Scrabble tiles, one for each letter of the alphabet. Shake up that bag, pull out a letter, that goes on your list. Put that letter back in, shake up that bag again, pull out a random letter, that goes on the list. So there should be no pattern in these keys. So all this stuff on the left, they're keys, but we don't have any data to use that. On the right here, we have our lookup table, essentially. This is like the rotation. So if you have a letter K, for example, that you want to encrypt and the key is L, you can use this lookup table to encrypt and decrypt. And we'll go through an example. I've got a text file open here to walk through this process to see what this might look like. So we are going to encrypt the word cat. So I'm a spy, you're a spy, I need to send you a message. I need you to tell you what animal has, the encrypted Bluetooth device. And so it might be the cat, might be a dog, might be something, whatever it is. I need to send you this message, CAT. So I'm going to look in my code table. And if we look at the first row here, we have, I know it's a little bit blurry, that's just the way, whoever took this picture from the NSA codebook, they weren't using a very good camera or scanner, whatever device they were using. So the key is LFHHY. Important that the key has to be as long as the message. My clear text unencrypted data is just 3 characters long, so my key only has to be 3 characters long. But if I had 1,000 characters that I had to transmit, my key would also have to be 1,000 characters long. So I pulled off more of that key than I needed to. I really only need the first 3 letters, and that's fine. So I've got the word cat. I've got the key LFH. So this is my clear, putting my arm around my microphone, clear text is cat. The key in this case is LFH. And then I've got my cipher text. What's that going to be? That's what we have to figure out, because I've got to encrypt this message before I send it to my secret agent compatriot. So we're going to use this lookup table to go through this process, and I'm going to scroll down. So the first character of the key is L. So I'm going to go to my lookup table and find that key L. My clear text, that first character is the letter C. So I'm going to use that lookup table. I find my key L, the clear text is C. So the encrypted data, it's just going to be in that column, would be M. So I'm going to replace that first question mark with an M. So what I'm doing, I'll scroll up. The key is L, so I find L here. I need to encrypt the C and cat, and so that corresponds to the letter M. All right, so far so good. I essentially rotated that letter C the amount L times. You can think of it that way. Now the next letter in the key is F. So I'm going to go to my lookup table in F. I need to encrypt the letter A, and that corresponds to the letter U. So the ciphertext will be U. And then the next letter in the key is H. So I'm going to go to my lookup table H. And then if I follow the same logic, I need to encrypt the letter T. So I'm going to substitute that with the letter Z. So using this one-time pad, the clear text message cat encrypted using the random key LFH produces the ciphertext MUZ. So why is this unbreakable? If you don't have the key, these three letters could literally be anything, any combination of letters. So if you can find a way, to decrypt that MUZ, not knowing the key, contact the National Security Agency. They would love to talk with you to see if you can do it. All right, so how do we decrypt? Let's decrypt some data. It's going to be similar to encrypting, but we're going to start with the ciphertext and reverse the process using the key. So the clear text, we don't know what it is. The key, we're going to have the key. We'll use the key, let's see, that's the last line in there, UGBOA. So my key is going to be UGBOA. And ciphertext. Let's make that a little bit prettier there. Okay, so what do I want to decrypt? What's my ciphertext? So we got a message. Spy sent us a message. The encrypted message is CFS. We know the key. I put 5 characters here. It turns out I don't need all those 5 characters. That's totally fine. I'm just going to delete those extra characters there because, yeah, we don't need them. All right, so we're going to reverse the process, essentially. So the first letter in the key was U, so I'm going to use my lookup table. So I go to my lookup table, I find the key U. I've got the ciphertext on that second row. It's C, and the corresponding letter just above it is the letter D. I bet you can guess where this is going at this point, but that's all right. The second letter in the key is the letter G. So in my lookup table, I go to the second row of the ciphertext, and that corresponds with the clear text letter O. And then the third character in the key is B. So what do? I go to my lookup table. The letter B says that the letter S, that's my ciphertext, corresponds with G. So I can encrypt and decrypt messages using this process. So it's not really hard. It's not a hard process to carry out. Is this really secure? Yes, in fact it is. If I gave you some ciphertext and I just mashed the keyboard, or I'll just copy this. Like, what could this be? RBB, TLF, DW, VKDDIL. That could literally be any combination of 14 character words. It could be multiple words. It could be dog, cat, pony, whatever. It could be send the file. It could be abort mission. It could literally be anything. There's no pattern because the key is random and because the key needs to be as long as that message. It's impossible to break this. Like, there's no program that you can run. There's no supercomputer on the planet. You throw every single supercomputer at this problem, it cannot crack it. It's impossible. With these 14 characters, that's how many different words or clear text messages we could produce using that ciphertext. So it's a big number. And we have no idea which one would be the right one, because we could create millions and millions of reasonable sounding clear text messages with no idea which one of them was correct. So just for example, among all of those trillions and trillions of clear text messages with different keys, with that same ciphertext, if we use these sample different keys here, that same ciphertext could produce 1 fish, 2 fish, or it could produce, with a different key, call me Ishmael, or with a different key, that ciphertext could produce it was a pleasure. So those are some famous books. Can you recognize those books? So if we were trying to brute force decrypt this, we would produce tons of reasonable sounding clear text without any idea which one was actually correct. So if the one-time pads are so secure, if they're amazing, and they're unbreakable, why don't we use them for absolutely everything? Why don't we use this for banking transactions? Like, I don't want someone intercepting my bank transfers and seeing what I'm doing with my finances. Why don't we use one-time pads on the modern internet? A thought question is, how do we distribute the keys? So let's think about this page. We have the NSA codebook. How do we give all of our secret agents these keys? And how do they agree on which key to use? Do we have a certain key to use at a certain date and time? Do we have a book? And on February 1st, we're going to use the codes on page 27. It gets complicated. Exchanging keys is tricky. Spies legitimately sometimes had these keys written on rice paper. And after they encrypted their message, they didn't want somebody intercepting that key, because if you've got the key, you can decrypt this message fairly easily. So they might use that key written on rice paper, then actually eat that rice paper so that key disappears. Now, hopefully, the only other person who has that key is the intended recipient, your fellow spy, in another country, another state, another city, wherever they might be. Because if anybody has the key, they can decrypt your message. So keeping these keys secret and aligning the keys and distributing these keys, that's one of the biggest challenges. Another challenge is that your key has to be really long if your message is really long. If you wanted to encrypt a message that, let's say, is 1 megabyte, your key also has to be 1 megabyte. What if your message is a video file and that video file is 10 gigabytes? Well, your key also has to be 10 gigabytes. That doesn't scale really well. It's not ideal for encrypting digital data and modern transactions. Works really well, but key exchange is the biggest problem. So, as a challenge, see if you can use the codebook to produce the ciphertext. Or, given the ciphertext, can you decrypt the data given a key? So one-time pads, they're good, they're secure, but there are different techniques that we need to use for modern day digital transactions.